So we are in HISIS now. So have you tried last week's work? Macam mana, okay ke? Ada problem? Okay, so senyap aja maksudnya okay lah kot. Okay, now just an overview, yeah. The production of acetic anhydride, that's what we're going to do today. The purpose of this lab is to install and convert a plug flow reactor. So from last week, what we have is a conversion reactor. So macam yang I cakap before, conversion reactor does not exist in real world. Okay, it is just for the purpose of making sure that the reaction proceed, and we fit in what's the we will fit in the conversion, and after that it will just calculate according to what we want. Okay, but in real life the reaction is depending on the kinetics. Okay, so in conversion reactor we ignored the kinetic part of the reaction. So say for example, if you did not have, still you have not have any information on the kinetics, so you can actually proceed with for the design of the whole plant by using conversion reactor, just by knowing how much is converted, that's all. Okay, but for the first part of your HISIS design, for your design project, we allow you to use the conversion reactor. But when you already once you have found all the information on the kinetics, then you change your conversion reactor to kinetic reactor. And just I nak pesankan lah, I nak pesan kat you so that you jangan tersilap. You have your design project. May I know what is the title for this semester? Title design project for this semester.
Chemical.
Apa dia, Afiq?
Chemical. Chemical product.
Ialah design project kan? You dapat tajuk design project semester ni? You semester 7 kan? Design project? Dah dapat tajuk ke belum?
Dah.
What's the title?
Tajuk lain-lain.
Yelah. Afiq tajuk.
Saya dapat air propanol, madam.
Izati dapat apa? Izati dapat apa?
Air propanol.
Air propanol? Okay. Aiman? Afiq?
Formaldehyde.
Formaldehyde. Atira?
Nitric acid.
Oh, tahu semester ni macam-macam jenis Haziq dapat apa?
Butadiene.
Oh. Ada berapa tajuk semester ni? Do you know berapa tajuk ada? Tak tahu No idea. Okay, fine. Well, I think those are the title that we have actually given to design project for your seniors previous years. So it can be done. It's a bit difficult. Well, it's not difficult. Something that you have to do as a chemical engineer. Kalau tak ada design project for chemical engineer, you tak dapat award chemical engineer. As a chemical engineer, you tak dapat degree. So because that's one of the requirement to become a chemical engineer, at least in Malaysia. And then in Malaysia, they follow Washington Accord, that is US certification, as well as ICAMI UK. So the degree from UK and the degree from US actually requires the students to have a final design project. So what we call as a capstone project. So that's what the design project all about. So yang I kata tadi, the one that I nak pesan lah. So when you already have your title, so you are going to look for pattern now. Okay, you have to look for pattern, the existing pattern, so that you can actually use the reactions. But when you are looking for the pattern, make sure you also found the information of the reactions in journals, so that you have the kinetic informations. because I've seen many students who actually chose a pattern, chose a process. The pattern I'm talking about is a process, bukannya the pattern of the plant, because you tak boleh tiru, you tak boleh ambil sebiji-sebiji the plant tu, or else you will be charged as plagiat. So that's why it's a very, very good idea. Once you have a reactor, once you have information of the process, then you develop your own plant. Then if you want to see the feasibility of the plant, then you can use HISIS. Okay, so now when you have decided to choose a reaction from a pattern, so you have to find the journals that describes the reactions, because you need to have the kinetic data. I've seen many cases whereby the student proceed with one particular reaction, and after that, masa dia masuk design project 2, they are not able, a person, one student will be responsible to design a reactor most of the time, because that's the heart of the reaction lah, the heart of the chemical reaction. So the chemical process. So someone will do the reactor, and that time when there is no available data on the kinetic, then he or she will be a dead meat. You see, because how can you proceed to the design without the kinetic data? While your group already decided long time ago, a previous semester, to use that particular reactions for the whole process. And so again, I pesanlah kepada the group, so you have to be responsible lah. Macam mana susah pun you kena cari. How you do it, this is a little bit of hint. Kalau you tengok dekat pattern tu, you found it, you can see a pattern, then dia ada author kan. So you cari author tu dekat paper of the authors dekat any journals. Maknanya kat guna Easy Access Library ke kan, yang dekat Science Direct tu. So you cari nama dia dan paper dia. So from usually before they come up with a pattern, they have actually produced or they come up with a pattern, and after that they produce journals from that, because and then the dekat journal tu they will describe thoroughly what's the reactions all about. Okay, so that's one hint lah. So don't select a process without enough kinetic data. So the kinetic data tu actually you have to find it semester ni, masa mula-mula, before you decide which process. Kalau tidak nanti don't choose a process without kinetic data, or else one of you will be in trouble. Okay, so you tak nak lah penanya kawan you kan, yang untuk semester depan. So the designing a reactor is hard enough, so without the chemical data, it's crazy. Okay, now what I'm trying to talk about this week, if you have a look at the question, the only thing that we give you here is the production of acetic anhydride. So again, the one that we are going to install in here is a plug flow reactor, because and then usually when you have a pattern, the only thing that they describe is only the reaction. And kadang-kadang dia bagilah sikit PFD but not the detailed PFD. So you have to come up with it. But you must have the information like this lah yang untuk your reactor. So just a little bit of overview. I've done this twice. Okay. Now let's close this one first. Each time I do it, I got it differently. So don't worry about it, because I think the first time I did it, I managed to converge it nicely. But last night when I tried it, this is what I got. So the only thing that is given in here is the reaction part. Okay, let's wait for this one to open. Okay, so this is what it's all about. Dia soalan dia satu je. Okay, so soalan dia hanya, it gives you this part. Okay, one of the route to produce acetic anhydride is by vapor phase cracking of acetone to produce ketene and methane. So now I know that my input is acetone, and from that it produces ketene and methane. The reaction is first order with respect to acetone. The feed to the reactor is 8,000 kilogram per hour. So I know the feed in here is 8,000. There you go. This one dah jadi 8477. I tell you why. Because I have recycle stream. Okay. But we can actually kita sebenarnya boleh adjust benda ni. But what you want when you have your design project, does not really matter what is the feed to the reactor, but what matters is the production. So this is the production of I don't know, probably methane or ketene sebab dia tak sebut. So this one I managed to get the methane product purity is 99.5%. Okay, so that's what I stated at the first place. So that's 99.5%. But then what matters, katalah this is the production, the methane production. So the mass flow is 899 kilogram per hour. So if you are katalah production, you have decided based on your supply and demand, you kata I want to produce this in, I don't know, India, you want to produce this in India, somewhere, I don't know, somewhere in India, but then the production is 100,000 metric ton per annum. So you have to specify the methane production 100,000 metric ton per annum, not the flow rate. So you have to do the back calculation. But either you do the back calculation based on the reaction and the conversion, or you can just let the feed in whatever you want. After that, you use the adjust button. So the adjust button would be here lah. Okay, the raw material here, because I dah kira-kira that is 3,200 because my recycle stream is 4,800. So initially this one has to be dalam soalan ni kata 8,000 kilogram per hour. But you have to back calculate lah how much is the mass flow, how much is the mass flow in here. Yeah, you can use the adjust button. I tak buat kali ni sebab because tak teringat. So anyway, what is given, kalau you tengok this is very similar to what you're going to get lah from your pattern. Dia akan hanya bagi the reaction, the information in here. So now it will give you the operating condition. So the operating condition of the reactor is 760 degrees Celsius and 700 kPa. So remember, this is a steady state process, so we assume that it is a perfectly mixed system in the reactor. So when it is a perfectly mixed system, we are going to say that whatever come out at the stream 5 is the same as whatever in the reactor. So when that happen, so the operating condition has to be set outside from the PFR, okay, not at the front. Remember this. The operating condition of all the equipments are to be set outside, because we are taking the assumption that everything is perfectly mixed in the system. So whatever come out is the operating condition is the one that is, even though that is a bad assumption for cloud flow, does not really matter, because we cannot actually set the temperature and pressure inside the cloud flow reactor. So this is only an estimation. Okay, now but in here, because of the kinetic reaction ni, kalau kita tengok balik dekat soalan, the conversion of the acetone is 40%, even though we use the plug flow reactor. So in this case, we suspect that this is either fluidized bed reactor or packed bed reactor. So those who take particle technology this semester, you guys are very lucky actually. So that is a subject not to avoid actually. That is a subject that you should take, because it will give you more knowledge on how to design. Even though many people say it is difficult, but actually it's not. Especially when you do your design, you dah besar kan, dah semester 7, dah semester akhir, tahun akhir. So I think you can see it better. So when you do your particle technology, you will learn a lot on how to design the packed bed reactor and the fluidized bed reactor. So when there's but in this case, this is a vapor phase kan. So this is actually the vapor phase. So usually you have a catalyst. So when you have a catalyst, then you must have information what are the sizing of the catalyst and the the voidage of the catalyst and things like that. So you must have in mind already what type of reactor that you want to use before you start your HISIS. So bila I baca ni, I rasa I tahu dah, because dia kata vapor phase cracking. Kalau vapor phase cracking, vapor usually it will involve a catalyst usually lah. So kalau it's a vapor phase with a catalyst, usually we use either packed bed, the two-phase packed bed gas solid, or fluidized bed. Okay, so and whether it is a packed bed or fluidized bed depending on the bed voidage of the catalyst. So in this case we use 0.5, so probably it is a fluidized bed, not a packed bed. Okay, simulate a complete process plan from the above information. The product purity needs to be achieved are as the following: liquid methane 99.5% purity. So in this case, I managed to get that 99.5%. Oh, I think I've shown it just before this. So liquid ketene. So what is needed 99%, but I managed to get it 99.9%, almost 1. Okay, so you can actually try to reduce it if it is too much, maknanya above your spec. You kena manipulate lepas tu. And then acetone, what we need is here, okay, is acetone, because this is a 40% conversion. So another 60% of acetone, even acetone is the limiting reactant kan, well that's the only reactant. So another 60% of acetone, you don't throw it away. So this is where it is. Kalau if you can see it here, no. The mass flow rate is 5,235 kilogram per hour. This is a lot of reactant to be chunked out. So it needs to be recycled back to your raw material as a raw material. So when you want to recycle this as a raw material, make sure the composition is the same as the one that is the raw material that you bought, okay? The one that you feed into the tank. So this is actually the recycle stream. So today I'm going to teach you how to do this recycle stream. And so now to tell you the story, the first time I buat dia jadi lain, the second one I dapat lain. The first time I buat, which I'm going to show you after this, I managed to separate methane, ketene and acetone only in one DC. But the second time I buat, I did it last night, I'm not able to do that. So don't worry about it. As long as what I can say about my reactor ni, my plant ni, because I've done it, I boleh dapat separation with high purity only at using 1 DC. So this process are not fully optimized. That's what I can say lah. But you know, I cuba banyak kali, banyak attempt. So just to repeat what I did, but I am not able to do that. So the first one is a multi-component distillation column. Then after that, this one consists of methane and ketene. Okay, ketene about 72%, methane about 27%. So from that, this is the second separation. Okay, so I think if I will use this reaction if this is a production of ketene. Why? Okay, if this is a production of methane is the main production, ketene is a byproduct. But if your problem statement, you are to produce 100,000 metric ton of methane, but then you are producing more ketene, you'll be in trouble because your main product is actually a byproduct. Kalau you tengok dekat the mass flow 899, I hope I'm right, 899, the mass product, ketene produces 2,342 kilogram per hour. So actually this is, I will put in here the production of acetic anhydride ni apa benda, kitin kot. Yalah kot. Yes. Okay. So betul lah ni. So you choose the right process sebab this is a production of acetic anhydride which is also known as kitin. So betul lah because this one actually produces a higher number of mass compared to methane. In here methane is your byproduct. So be careful when you choose your reaction for your design project. So now this is what I've done. So what we have from the question only this, you are to develop the whole thing. At the end of the day, when you have a reaction, then of course you have to develop the whole process plan so it is feasible. Any questions so far before I show you the second part of what I've done to get the separation? Any question ke?
No.
Ada? Okay. Ke tak buka mata lagi ni?
Dah buka dah.
Tak ada?
Dah buka dah.
Okay. Oh, come on. Open. Tadi was extensive. Okay. No. Version 2. No, I did version 2. Okay. So ini rupa dia. This is the one that I did where I managed to separate. This is methane. So that is 99.5% product purity of methane. So this is 99% purity of ketene, and this is 99.99% which is close to 1, the recycled stream of acetone. I do not know. I have tried to repeat this, but this is difficult to kena sabar, kena buat step by step sebab dia buat iteration kan. So bila iteration tu dah lari jauh, dia dah tak boleh nak go back to the actual one. If you're lucky, you get this. So the keyword in here is kesabaran. You have to sabar. When you do this, cuba banyak kali, berapa kali I delete, and then bila kita buat the DC pun, I think the first step I did was I choose total condenser first, where both methane and ketene would be in one stream, and after that once it's converged, kita tukar kepada partial condenser, because your methane is the most volatile compound. Dia akan dapat as a vapor. Kalau you perasan yang tadi pun actually you will get it in vapor, because I mean yang the last DC, the second DC tu, the second DC to separate methane and ketene. So you cannot actually do it as a total condenser for that, because the temperature difference tu, I tried to find the pressure drop that is able to separate it from in a liquid phase. I'm not able to do that. So this one is something that you have to. So benda-benda macam ni you have to try many times. Okay, you have to try many times whether it is at total condenser or we use it as a total condenser or partial condenser like this. Okay, so let's start. So I would suggest you start dengan this one first, and after that you go back. That's why I do in here. That's why number dia macam pelik-pelik lah. Numbering dia macam pelik because actually I studied from here. Ni ada tukar numbering. Asalnya ni nombor 1 kat sini. So we try to do that, and after that we need to develop the whole thing like this. I hope we can do that in 1.5 hours. Okay, are we ready?
Yes.
First case. I can give you the output of my high cis tapi I can give it to you in I can letak dekat dalam one of the PC, then you can just save it kat situ. Nak ke? Do you want it?
Boleh later.
Later, kejap lagi I buat. Mungkin PC nantilah dekat laptop. Nanti I'll let you know dekat PC mana.
Alright.
Probably I just copy dekat my link, dekat my drive kot. Nantilah tengok macam mana. So you just ambil daripada situ. Okay, now let's do this. Acetane, methane, and ketene. So let's add component. Methane. Now the next one is acetone. And the next one is acetic anhydride. Anhydride. Like the component. So bila dia tak recognize like that, so what you need to do is you have to change it to the formula, and we type in the formula C2H2O. So it's ketene, C2H2O. Kenapa dia ada carbomethane and ketene? Carbomethane and ketene. It's just the synonym. So that's not really matter. Okay, let's choose this one. Okay, now we add this. Then we're going to add the fluid package. So in here, I want you to use Wilson Pine Robinson, because we're going to have both vapor and liquid. But you are free to use Pine Robinson, does not really matter. Okay, Wilson, and let's choose the vapor model. Don't leave it to be ideal, because if the pressure involved in the system, pressure of vapor, kalau ada somewhere more than 10 bar, then dah deviate daripada the properties will deviate, because you are not using the right equation. So let's use Pine Robinson in here. Okay, we are good. Wilson, before that, because you are using the activity coefficient model, so you have to go to binary coefficient. So dia tak ada the interaction between the other molecules except for acetone and methane, and methane and acetone is the same thing. So now let's estimate it, all binaries. So this has been estimated except for acetone and ketene, tak ada. So probably this is not a good equation of state. Not a good activity coefficient model, but you can explore more after this. So, but for exercise purposes, let's continue with this. So we are done with reaction and basis. So another one, we have to put in a reaction, because this is a reactor. Now you go to add reaction. So the type of reaction that we're going to use this time is kinetic. Last week we used conversion, because it's only conversion reactor. We just put in how many, what are the percentage that we want conversion. But now it's kinetic. Add reaction. We close this. So when we choose kinetic reaction, okay, you have this information: the the activation energy, and the alpha. Okay, to calculate the kinetic. So this is the equation that we use to find. This is a normal equation lah kan. So add component. So we have methane. We are going to add acetone. We are going to add ketene. And then we follow the stoichiometric coefficient. For methane, it's +1, because that's a product. And then acetone is -1, because it's a reactant, and ketene is a product as well. Okay, now it's empty. This is fine. Then we have information in here in the question, the forward reaction for alpha, A 8.2 to the power of 14. So we put E14, and activity coefficient, activation energy 2.85, E5. So we enter. So it's ready. Okay. Now we go to before that. Now this reaction, kalau you tengok dia ada macam ni. Okay, maknanya it is not being attached to fluid package. We have created the reaction, we call it as reaction 1, but we have fluid package and component is attached to fluid package, but the reaction has not been attached to the fluid package. So what we want to do is we add to FP, add to fluid package, then we are okay. Now dia dah jadi tanda tick kat sini. So maknanya it's ready. Now we go to simulation. Okay, so we bring in the stream. We want to do plug flow reactor, isn't it? So let's do it for reactor first, and after that we develop from that. So we want to do reactor. So we type in plug flow. So this is what it looks like, plug flow reactor. We bring it in. So we will start to attach this. Oh no, before that, let's specify what is our number one ni. So the composition. Now, acetone is the only molecule dekat sini. So it's 1. Okay. So that's 0. And that's 0. Enter. We are okay because the total is 1. We are okay. And then the pressure. Okay, now can we put in the pressure in here because there's operating pressure. Ataupun you boleh agak-agak je, does not really matter. Yeah, I think so. Let's try this. I tak pernah try letak temperature and pressure from outside. 760 and the pressure is 700 kPa. Dia akan back calculation. I hope so. What else? Oh, the flow. Okay, now the flow in here is 8,000 kan? Okay, let's see if we can do this. Okay, 1. Banyaklah benda dia suruh kita suruh dia kira. Ada energy tak? We can actually put in the energy. It's Q100. Okay, now the information in here is reaction. Reaction set to be attached in here is set 1. Okay, yang tadi kita dah specify tu. Okay, now if you want to look at the details, this is okay. Now, look at the parameter. We have to put in the delta P. But when you're using a plug flow reactor, when you do your, bila siapa yang belajar particle technology, then that's an equation that we can use to calculate the pressure drop. That is what we call this Ergen equation. So I'll just put in Ergen equation. Okay, now unknown dimensions. We have to actually estimate the dimensions lah. Berapa dimension of this one. Like we can put it as a single phase because it's only a single phase in here. That is the dimension. Terus sabar agak cari benda ni tak jumpa. Rating. Is it rating? Here you go. So kalau dekat soalan dia ada kata first estimation use assumption of as the following. So you have to tell what is the dimensions of your plug flow. So your length, let's put it as 2 meters and your inner diameter as 1 meter. Tengok unknown duty. Kenapa nak unknown duty? Because I already put in the temperature. Okay, now boleh tak kita padam ni? Tengok macam mana. Yes. So boleh tak? Not solve. Why? I think dia pening. Okay, now let's delete this. Just tak pernah try. Nanti kita tukar, kita estimate. Because we're talking about the operating temperature kan. Operating temperature and pressure. So the pressure, just put it first and after that you check it. I don't know, 720. Just estimate lah. And temperature, just put it 760 and see how. So it is converge. What's the temperature? Sama. Dia consider this is an isothermal process. So does not really matter. Unless if you want to put in Q in kat situ, you can actually set this one at 720. Does not matter. But this is pretty hot. Actually, you should have a Q in. Tell you what. Usually what happen is that I think I buat salah tadi dekat my previous punya ni. 760 is fair. Usually kita preheat our product. what we call this, kita preheat our flow in ni. So let's put it as 300 if it's working, and after that we attach this Q100 and we put it as 760. I think this is the correct one. 760. Okay, now what's the pressure? Kenapa dia tak kira? Okay, now kenapa data pilih kosong? Oh, I know what's the problem. Because we put it as a single phase just now. It's not single phase, it's a two-phase flow. So kalau single phase tengok void fraction dia satu. That's why dia jadi salah. Where am I going to get back? Sign. Mana tadi nak klik single phase pun dah tahu nak cakap mana. Here you go. It's a two-phase. Sebab dia ada solid dengan liquid phase. Solid dengan vapor phase. Because we are using a catalyst. Most of the time when it's a vapor phase, dia guna catalyst. So if there is no catalyst, then you can use single phase. Okay. So if not, we use okay. Now, so when this happen, kenapa? It's to 0. I don't know. We should be calculating. Okay. The void is specified as 1. Kat sini, the void fraction. So this is a tube packing. So if this is a fluidized bed or packed bed, kalau packed bed usually the packing is about 0.3 to 0.4. Kalau it's a fluidized bed, usually it's from 0.5 to 0.7. Usually lah, the void fraction. Void fractions means that the void between the catalyst tu. Okay, the void between catalyst, but in this case, let's estimate to be 0.5. It's operating below, probably at, apa dia panggil? UMF, minimum fluidization velocity. Okay, so let's assume that void fraction is equal to 0. Now, we are done. So kalau you tengok dekat your design, you ada calculation of Ergun equation. Okay, it's 23 kPa. So okay lah. So when you do your design, probably you can get this as the estimation. Okay, let's check the reaction. So the results in here, the reaction says 0. I really hate this when this happens. Interesting. Zero reaction. So actually there's supposed to be some value in here because we need to do the adjust button later on. Set 1, this is correct. So this is correct, this is fine, this is fine. Never mind. Let's just apply our adjust button in here and see. 760, 300. Let's change this one to 760 and see what happens. 760. Let's see if this is isothermal and what happened. Still kosong. It's not really matter. So let's estimate this one to be at 300. Kita preheat dulu benda ni. Tadi 300 kan. Okay, let's do the adjust button. So select variable. So kita select variable. What we want is that dia tulis kat sini, you have to okay, the length and inner diameter can be changed to achieve the goal of 40% conversion. So means that the conversion of your reactor depending on your size, okay, for plug flow. So when you do your design, if you were to design your punya fixed bed or fluidized bed, make sure it's you adjust lah dia punya diameter. You get the, selalunya is in the tube dalam pipe, dalam bentuk pipeline kan, pipe berapa 15 cm each ke macam itu. Tapi in this one, we assume that the number of tube is equals to 1. So let's select the variable. So the variable that we want to change, it is PFR 100. So you choose this one. And after that, we want to change the tube length. I just fixed the diameter at 1. Tengok macam mana. Okay. And after that, you select the variable also PFR 100. And we want to change the conversion. So that is actual percent conversion underscore 1. That's what it called. And let's put it to be, kita nak 40% kan? 40 because conversion is in percent. Okay, kita tukar ni kepada 1000. Just I don't want to be asking me many times. So let's start. I hope you got it. Aku tahu kenapa tadi dapat kosong conversion, patutnya ada some value. Don't tell me this is not solving. Not solving. Shoot. Yeah. Excuse me for this. Delete semua. So let's put this as 700. Mungkin it's not working like that. I don't know. Adalah yang tak kena ni. Mana part flow I? It is not. Oh, that's pipe segment. Okay. Ada you all nak tanya soalan ke sementara buat benda ni? Okay semua? Pening?
Slow sikit tu.
Apa yang slow? You all slow ke I slow?
Saya slow.
Slow nak absorb benda ni?
Banyak
Banyak benar ya? Apa, cuba
input.
tanya kat I soalan apa benda you rasa you macam, mesti banyak soalan dalam kepala you ni. Banyak soalan, I tahu banyak soalan. Tanya je lah, soalan bodoh pun tak apa. Tak ada siapa nak gelak kat you pun. Sama je semua. Apa soalan dia? Ada soalan?
Setakat ni okey je.
Slow, tak faham, lepas tu okey. Macam mana tu? Alamak, manalah pergi tadi kat I punya rating tadi tu. Rating kot. Oh yes, okay, the length kita letak. Jadi berapa? 2 2. Cuba tanya kat I, apa benda yang you tak faham, benda-benda yang I letak kat sini. Apa yang you tak faham? Ada tak benda yang you tak faham? Tak ada soalan Steady je semua. Oh ni 3270 dah lain pula pressure drop dia. Number of steps. So, okay now. So this is, I just tell you some information on the crystal data, catalyst data. So particle diameter catalyst yang you guna kat sini adalah about 1 mm. And then the particle sphericity is 1, means that dia bulat, betul-betul bulat. If it's not bulat, then particle sphericity ni boleh bertukar. So you know your catalyst that you want to put in. So it's a solid density. So I think this is a good estimation. And the bulk density is fine. Usually you can find the information, all of this information for your catalyst. And then solid heat capacity ni tak apa, biar je kat sini. Or if you have information, tak apa, you boleh masukkan. The bulk density is something that they calculate daripada sphericity, particle diameter information and solid density. So this is done. Let's look at results. Kenapa kosong? I don't know. I hate this when this happens. don't know why zero. Sales, this is fine. Result, design,
Doktor tengah nak adjust apa ya tu?
Nak conversion. Sekarang ni reactor ni dia converge.
Okay.
Tapi tengok result dia, reaction, results, nothing going on. Maknanya acetone keluar, dia tak ada reaction.
Oh, okay.
I silap kitin tadi ke? I don't know lah. I don't know. Is it this one? C2 H2O. It's the same thing. Kalau tidak mesti dia keluar yang tadi tu. Ketin mono apa benda tu. Nama sinonim tu. C2H2O. This is correct. Alah leceh lah. Apa mesti jadi masa ni pula. That's fine. Or else dia tak boleh attach to this. Reaction ni betul ke? 8.210 2.85 10 kilojoule per mole. This is kosong. There's no reverse reaction. This is all correct. Kalau tidak dia tak boleh nak converge. Why I zero? This one detail reaction methane acetone ketene. I know why. I'm so stupid, sorry. You nampak kat sini? Base component is acetone, reaction phase is liquid phase. So what should it be? You guys? Vapor kan? That's why. They are trying very hard to do the reaction at vapor phase, but then kita specify liquid phase. So this one has to be vapor phase. Oh, I'm glad I made this mistake in front of you guys. Kalau tidak, you all takkan perasan. Okay, now your results here. See, 22.99.
199.
Okay, very important benda tu. Very important. So now we want the reaction to be 40%. So now we bring the adjust button in here. Then again we do it PFR. So kalau kosong reaction tu, something is not right with your setting lah, definitely. So check back the information. Then let's assume that we fix the diameter, we change the tube length. So select, and then the select variable, PFR, conversion, select, and then let's make this one to be 40%. Let's go to the parameters. Tukarlah 1000. Now we can start. Aku lambat pula, semalam cepat ya. Sekejap. Kita stop ni, tengok apa jadi. Dia jadi benda pelik-pelik dah ni. Dah jadi sampai 30% dia tak sampai 40% sebab dia beli sekejap
Hello, madam.
Hmm?
Macam nak tahu benda apa, variable apa yang kita nak kena tukar supaya kita dapat variable yang kita nak, contoh for this case kita punya conversion tu.
40%. So sebenarnya you boleh tukar variables sekejap. I pun tengah fikir kenapa masalah ni. Okay, now the one that I want kita kata the variable that we can change in this case is the size. Okay, the size of the tube dimension. You can actually manipulate this. So also and the void fraction. So let's try if we can do that. I tak tahu kenapa that's not converging. This is weird. Apa silap kat mana information yang I lost. It's not converging. So untuk plug flow reactor, you can actually tukar void fraction. You can change the length and the diameter, which is the size. And if you know the information of particle size semua ni, then you can do that. Hai, sejam buat reactor pahal ni. Yes. Pressure dah jadi 80. Salah pressure ke? Oh, the pressure change tu dia jadi besar because pressure 720, temperature is 760. Let me change this. Dia dah silap kat sini, dia ni sebab kita guna, patutnya boleh guna Eigen equation, so that's not really matter. Let's do this. I estimate about 20 kPa pun kalau guna Eigen later, kita tengok macam mana. So the rating, this one let's do 2 meters. So pressure out, the temperature out in here is temperature 632. Right. So I think why not we add a heater in here. So this is exothermic reaction. Okay. Wow, 97.
Doktor,
Yep.
yang number of tubes tu memang satu je?
Kita assume dulu satu. Kita assume dulu satu.
Okay.
Solve. Energy kena masuk. This is fine. 40%. Okay ke? Tanya soalan. Apa benda nak tanya soalan? So kita assume satu. Let's start next time. Kalau you dah tahu some information, you boleh letak number of tube tu to be berapa lah, 10 ke 100 ke dan dia ni kan. Kalau you kira pun you can get it 100 macam tu. Sebab you pack the tube, you pack the catalyst in the tube, especially when you want to do a pack bag. Kalau fluidize bag rasanya jarang ada tube tu. Selalunya dia one big thing. Tapi this is only an estimation. So you got this already. So now the operating condition in here is the pressure is 700, temperature 760. So if you want to be accurate, then we can try to change this to Ergen equation and see parameters, Ergen equation. So dia dah boleh kira sebab once let's see, boleh tak dia kira. So the pressure drop is only 4, actually 4 kPa. So the pressure in here is 715. So kita nak 700 kan. So kita take out lah. Berapa? 60 tolak 15 apa? 745, betul?
Betul.
Tak silap. 706. This one 760. 745 kan? 705 lah kan? Pressure 700. Dia punya temperature 760. So now, so you have done this. So sekarang ni, you cannot leave it like this because you are not going to get your raw material like this. Okay, let's see if we put in temperature 400. Now, your feed stream would be not going to be in liquid phase, vapor phase. So you can do it in a liquid phase. Okay, so what we do is that we bring in a stream. So the pre-preparation of material before it enters your reactor ni you kena buat. And you know you'll have recycle stream because only 40% is converge. I mean 40% aja yang oh my god. Yes, converted. So now we know we must have a tank. Oh sorry, this is separator. This is only a separator. Now we bring in a tank. Okay. Nanti later on kita akan fitkan kita punya recycle stream. So this one must have kalau tank dia mesti ada dua feed. Ya, ada dua out. So we masukkan yang 3 ni. Vapor outlet is 4, liquid outlet is 5. You can put in energy if you want to, but probably we don't need to do it now. Later lah kalau you rasa ada energy nak kena tambah. Now we go to composition, then we know our methane is acetone kita 1. Okay. Okay. So we are okay, acetone and the rest, maknanya this is your raw material lah. Okay, the mole fraction is 1. And the composition we can actually take out yang tadi tu, yang the one that what we want, that is 8,000. Lepas tu nanti kita sambung aja. 8,000 kilogram per hour kan. Okay. So in this case the pressure, I don't know, 3 bar. The pressure is 3 bar, the temperature 25. So that is what we have, the feed lah ke dalam yang ini. So the temperature 25 acetone dia memang dalam liquid form. So why buy something at a high pressure with a vapor phase while it's much better to store everything in liquid phase. So in here is 0, so you can always hide this or you can delete that. Not an issue. Yes, we can delete that. Oh, tak boleh rupanya. Delete dah pula. Hide lah, hide. So let's hide this. Okay, once you have this, okay, now the pressure here. Oh, let's put in kita lupa nak put in the pressure drop inside the tank. So the pressure drop, we go to parameter. I don't know, 30 kPa, 50 standard lah, 50 kPa. Kalau you rasa 50 kPa besar sangat, then you can always change it. It's not an issue. Now, we have to actually vaporize this. How are we going to do it? What is the equipment that we need?
Superheater. Boiler.
Boiler. Okay, now.
Vaporizer.
Yep. Why not? Yeah, vaporizer. But there's no vaporizer in here. So what we have is only a heater. Whether you can put in heater or we just put heat exchanger terus. Nah, kita letak heat exchanger. Okay? You dah pandai kan buat heat exchanger? Ke nak guna heater dulu? Kalau guna heater, later on boleh tukar. So kita buat heat exchanger. Nantilah kita buat heater lah sebab nak cepat. Tengok ada masa ke tidak nanti. Sebab takut tak cukup masa. Pada numbering issue, I letak heater dulu. Okay, 5, 6. Dia tak ada boiler kat sini. Dia ada furnace tapi I tak pernah guna. Reboiler I tak sure, tak pernah explore. I always use heater or heat exchanger. Senang cerita. So now we have our energy. Q101. Unknown delta. Berapa delta P nak letak kat sini?
10.
Ha?
10.
10. 30 lah.
30, okay.
Nak vaporize ni. Unknown duty. So okay, now we need to check berapa temperature everything is vaporized. So we put in dekat sini berapa? Anyone?
1.
Correct. Because we want to see what's the temperature. But we don't want it to be condensed sebab lepas ni you kena naikkan pressure dia. Okay, sebab the pressure to the reactor is 760 kPa kan? 700 kPa. So kita tak nak, we don't let it be at 1 because we don't want suddenly it condense in your compressor. Lepas tu dia rosak lah. So we know the temperature has to be more than 80. So let's change this to it berapa nak? Anyone? Afiq? 90? 100? Izati? Berapa nak letak sini?
100.
Berapa?
100.
100. Ikut suka you. I ikut cakap you tau. Okay, the vapor phase. Okay, now. So the temperature in here is already at vapor phase, but then the pressure is 220. So this one, the required operating pressure here is 700 kPa. So what are the equipment that we use? Aziz? Syamil? Baik, Kak Kelak, you kena ready microphone. Berapa apa equipment yang akan letak kat sini because I want to increase the pressure.
Compressor.
Compressor, thank you. Okay, we put in the compressor in here. Tapi sebelum kita masukkan ni, kita tengok what be the temperature, the pressure, what is the temperature like because tadi kita set dekat sini the temperature 760 kan. Okay, that is the operating pressure. Operating temperature for the reactor. So operating temperature for the reactor has to be set kat outside sebenarnya. So nanti kita adjust. So now before kita add semua, why not we just put in a stream there, and then we put in 6, that is 7, kita tengok output dia berapa, later on kita delete 102. Okay, unknown duty. So kita kata kita nak pressure jadi 705. Alright. The pressure 705. 705 kPa. So the temperature is 158. So let's see if we put in 158 dalam ni, will we get 40% conversion? But remember we have Q100 kat sini. Okay, dia exoprocess tapi this is exoprocess. So bila this is exoprocess, sekejap let me think. 760 dia ada heat negative. So this is exoprocess, this is coolant. So kita tak boleh nak expect benda ni to heat it up. I don't know. So probably we need to increase the temperature in here. Okay, we need to increase the temperature in here. Kalau tidak, you can try tengok macam mana dia balance up the exoprocess and the endo in here. But I takut dia akan ada issue. Later on dia boleh buat the optimization of the process. Sekarang ni, let's increase this to, I don't know, 400 degrees Celsius. So this is 467. So let's delete this one. Bismillahirrahmanirrahim. Yes. We include this to be 7. It converge. Sebab adjust button still there kan. Kita tengok. The reactor, the reaction, the result still 40%. So let's look at the temperature. The pressure is 676, temperature 760. So the pressure has to be increased to 700 kPa. So 720 kot tadi. 704 705 lah. Cuba tengok what happened here. Still, so mungkin boleh guna adjust button to do that. Can we try that adjust button again? So adjusted variable is what? 7 kan tadi kan? You tahu kan apa? Do you understand what I'm trying to do, right? So that's the pressure. Select. And targeted variable is 2. So that is also our pressure. MNOP, pressure. Select. So we want our pressure to be 700 kPa. Tak start lagi. Parameter 1000. Dah. Okay. So that's 700. Let's check. Yang penting is the conversion. The results 40.57. Okay lah. Sebab dia ada 2 adjust button kat sini. So the temperature, the pressure is 7 to 7.4. So boleh lah kalau you nak buang benda ni dapatkan 30% pun is 40% also can. Boleh lah 40.5. You faham ke apa I buat? You all?
Faham.
Faham Okay, good. Okay, now the other challenging part. How to separate all this? Okay. So now the composition in here. So we have, I tak suka nak tengok in mass fraction sebab mole fraction sebab I tak kerti nak estimate. So I always look for mass fraction. And then okay, now we have 50% of acetone left, about 60% acetone, ketene 29% and methane. Okay, now I tried before using separator actually, to be frank with you, because I was thinking that if I can if I can get rid of methane awal-awal guna separator, then I can actually separate acetone and ketene by using distillation column. Okay, because separator is much more, it's cheaper compared to your distillation column. But the problem is that the story of methane is a bit complicated. Kita tak the color, if you can still remember, in separator you can actually adjust it by using the temperature of the the temperature of the separator tu, so that we thought that we can actually separate methane dengan acetone dan ketene. But I've tried that before. You boleh try and see what's the effect. But I've tried before dan methane dia still present dekat acetone dan ketene punya liquid stream. So when it is more complicated like that, I managed to actually separate methane. Tapi there's still methane in acetone and ketene. So what's the point of doing that? Because when there's methane and dekat acetone and ketene dekat liquid form out of separator, still I need a multi-component DC dengan the next one is binary DC. Might as well I just put it in a DC. So obviously kalau you tengok dekat the component stream, now let's look at property again. I just want you to check later on. So methane, the boiling point is -161. Because you nak susun which one is the more volatile component. So you nak tahu which one to be collected dekat top, the bottom and so on and so forth. So we look at the normal boiling point of each of these component. Then kalau you tengok methane, the boiling point is -161. Boiling point for ketene is -41. Boiling point of acetone is 56. So kita tahu the most volatile is methane. Then acetone yang akan jadi bottom product. Okay, kalau kita buat multi component DC. And ketene would be the distillate. Okay, tapi I tried buat DC, multi component DC, but I managed to separate all these three. But I'm not going to show it today because I'm not confident I can finish it by 11 o'clock. By 10:30 kan, 10:30 or 11 macam tu. So let's kita buat aja guna DC biasa, and after that if you want to try to optimize your DC, mungkin we can actually buang satu DC later on. So with this knowledge, we close this. You go to simulation again. Now let's bring in your DC. This is your DC. Now we plan for total condenser. Oh, before that, this is vapor stream kan? The pressure is 700. I don't know, hari tu I letak valve. Ada yang tengoklah dekat dalam I punya example dekat lab ni, I letak expander. Okay, now beza you letak expander or beza you letak valve, because you want to see whether the temperature change tu, can you afford to lose temperatures out of it. Because kalau you guna expander, some of your temperature will be, dia akan ada temperature decrease sedikit. But if you couldn't afford, bukan sedikit, quite significant lah. Macam dia macam compressor kan. So expander dia, tapi dia kurang sikit, temperature would be the opposite of compressor. But if you cannot afford to lose the energy from the stream, you guna valve. Okay. But I dah buat benda ni banyak kali, so I think this one will work at a low pressure system and low temperature. So this one, you can actually do it at vapor phase. Does not really matter. Maksudnya your Q untuk dissolution column would be equals to 1 kan. Kalau liquid, Q is equals to 0 kan, kalau tak silap I. So Q is equals to 1. Jadi when you do this but temperature set 760 is too much, dia akan, because you need to bring this on to minus something. So your utility dekat condenser, dekat reboiler ni will be very high. So if you want to get the success of how to separate this, so you have to bring down the temperature and pressure. So I think the first time I buat, I guna expander, but this time let's use valve and heater. Cooler. Sekejap cepat lepas tu nanti boleh buat the optimization So you can do this and then it's cooler. Cari dulu. Okay, now kita U103 dulu. Kita ambil lah valve ni. So yang keluar 2, outlet 1. Tadi kita dah delete kan, that's why dia keluar balik. The parameter, I don't know, pressure drop berapa? Anyone? 0. Berapa? Anyone?
10.
Okay. Suka. Estimate apa pula? Pressure drop 10. Sorry. Valve lah. So, silap. I thought it's a heater. Aduh ni. Dah bergulung-gulung lidah I cakap ni tahu. Parameter salah ni, di pressure takkan nak turun 10 bar letak valve kot. 10 bar pula, 10 kPa. So let's bring this down to, I don't know, 4 bars, 3 bar, 4, 3, 4. Usually flow biasa about 3 to 4 bar. Sebab kita nak ada pressure daripada depan tu. Okay, let's change this to 350 kPa. I don't know, try this. So the temperature, kalau you tengok temperature and before and after valve ni, dia tak banyak beza. Dia about 0.3 degree Celsius difference. But then kalau you guna expander, then you akan ada temperature change significant. Okay, now let's put in 1. Let's outlet is 8. The energy is Q103. Right. So now, you need the temperature in here. Sorry, sebelum that you need a pressure drop. Macam kita kata tadi, I don't know, 20 kPa, 10 kPa, 30, itu sekolah. Lebih kurang. So now, we still can maintain this to, let's for fun, let's change this one to 0. Nak tengok what is the temperature for everything to be liquefied. Minus 168.1. So we don't want it to happen here because we need not to force the feed to the distillation column to be in liquid phase. It can be in vapor phase. Because kalau you nak turunkan daripada 700 plus kepada minus 168, you punya utility dekat heat exchanger ni, padahal you have another utility needed because at the end you ada boiler kan, you still need to evaporize everything, and then after that you have to condense dekat condenser. So I don't think this is wise to put it in liquid phase. So we can actually lead it be at a vapor phase. So kita akan tukar you punya temperature tadi. So whatever above minus 168 would be your in vapor phase. So you all nak buat apa? Berapa temperature nak set ni dekat 8 ni? Anyone? Dekat 8 ni. So that it can remain as a vapor phase.
Kalau room temperature ke? Boleh tak?
Room temperature
35 ke 30?
boleh, tapi utility tinggi lagi lah.
Itu dekat vapor phase.
Boleh, tapi kalau you dekat 30, utility dia dia
tinggi.
mix.
Oh,
Dia
yes. Sebab from 700 kan?
Dia pun mix. Sebab boiling point untuk acetone tadi 68 kan? So it has to be more than 68.
So,
I don't know, 200, 100.
200.
200. Just kita buat macam tu je lah, kita tengok. Because this one, the temperature inlet will actually affect your separation efficiency. So you can actually change your temperature inlet ni berapa. Okay, your pressure difference you can always change it dekat dalam reactor ni, dalam distillation column. But this one will give you the effect lah on the efficiency of this. Okay, let's do this. We have another half an hour. I hope I can finish this. 8. Let's decide on total condenser sebab kita nak cepat. You can actually change this. Okay, let's change this to, I don't know, 20. You can manipulate number of stages and the inlet stage ni untuk mendapatkan product purity. Does not really matter. Okay, now let's go next. Pressure drop. Pressure drop at the boiler. Berapa? 20, 30, 20, 10, 20. Macam, tak, mana boleh. Okay, inlet tadi 3.5 kan? 3.5 bar. So the reboiler pressure berapa? 2.8? 280 kPa. This one, I don't know. 150 kPa. This one, pressure drop 10, 20, tu sukalah. So this one 20. The next. Okay, next. I don't know. I just put it here. 3. I don't know. Okay, dan nanti kita estimate je. Tengok untuk dapatkan the first estimation. Right. Okay, now we need the information in here so that this is a DC. I just don't care what is the information inside as long as I dapat acetone I dekat bawah ni purity 99.99%. We cannot put 1 because dia akan kata over the limit, maximum limit dia. So basically if you want it to be read as 1 is you have to put it 0.9999% because HISIS ni dia punya tolerance after 4 decimal places dah jadi tolerance dia dah jadi macam taking it as 1 lah. Okay, what we need to add spec in here because we want to make sure that we got the acetone at the component acetone yang dekat bottom tu as pure as possible. Now the stages, make it a reboiler. I like to set it a reboiler. The mass let's work with the mass fraction. Dekat reboiler, let's set it to be vapor phase. The component is acetone. The spec value is 0.9999. Okay, enter. So let's make this as your active, and this is degree of freedom is equal to -1. Distillate rate we just don't care. Just so dia pun dah dapat 0.999. Refract ratio I 3, does not really matter as long as I got this. So let's check the composition. As long as the composition is okay, does not really matter what is your estimate untuk refract ratio you. So let's do this. Composition. Here you go. I got 1 mass fraction I. That's right. So dia sama dah dengan macam raw material. So let's look at your nombor 9 ni. the temperature, dia ada sedikit vapor phase, nanti dia ada problem nak masuk dalam compressor. The thing is that because your pressure is 1.5 ni, I takut unless you want to operate your second DC under vacuum, you can do that. You can do that, but then you need a jet vacuum lah nanti untuk the second DC. Usually we use vacuum DC because kita nak protect kita punya dekat reboiler tu. If the pressure is too high, the temperature, katalah the temperature at reboiler it goes crazy like 300 degrees Celsius macam itu, it can actually destroy your component, your compound. Okay, dia akan, compound tu akan deteriorate, bukan deteriorate, dia panggil apa dia akan pecah lah. Molekul kan, compound consists of molecule structure. So the molecule akan break. So dia akan decompose. That's the word. Dia akan decompose dan dia rosak. So we don't want that to happen. So when this is the case at reboiler tau. So bila the temperature at reboiler is too high, the pressure is too high, then you need to bring down the boiling point of the component at reboiler to be lowered. So when you want to do that, you can actually make the pressure to be in vacuum. Maknanya less than 1 bar lah. 0.5, 0.3 bar, something like that. So with that, your temperature or the melting temperature tu akan turun. Jadi turun lah, especially heavy compound. So when you do that, then you protect you punya compound yang dekat distillation tu, dekat bottom tu. So that's the reason why we use a vacuum distillation column. I think you dah belajar benda-benda ni kan dulu. Now we need to increase, kalau I akan increase sikit pressure ni because I want to, I don't know, you have to make benda ni kena buat economical punya. Let's see what's the composition in here. You kena decide. Now it has a equimolar. Dia ada equimolar, mole fraction dia equimolar. Sebab mole fraction is equimolar because tadi daripada reaction tadi kan, dia 1 to 1 ratio. So if we change it to mass fraction, then we can see that ketene is higher 70% than methane. So this is in liquid phase. So I want to increase the pressure. So let's put in pump in here. Let's increase the pressure, I don't know, to 3 bar. Ini you have to remember, this is not the end. Ini bukan finalized simulation tau. You still can do a lot of optimization in here so that you can reduce the energy usage and things like that. This is the purpose of this class. Dengan masa yang singkat ni, I can only show you what can be done. The rest will be up to you. Use your common sense and all the knowledge that you have learned before. Okay, rasa pressure tak tiba-tiba je Ni kenapa pula tak mau converge isu ni. Vapor in inlet stream. Dia ada isu sebab ada vapor. So there should not be any vapor in inlet stream macam I cakap tadi. I saw it there. No, where is it? I saw it there. Okay. So what you have to do is reduce the pressure. Let's reduce the pressure in here to 130 kPa. And see if it can condense everything. Dia tak mau. 100, 130, 150 ke lagi naik 180 kot. Maksudnya when they increase the pressure in dekat condenser ni, okay, condenser ni 180, jadi everything dia effect lah you punya this one. So tadi dia tak boleh nak converge because dia ada vapor. Vapor will actually destroy your your pump so dia tak nak enter kat situ. So now the pressure is 3 bar. What do you want to do now? Oh, sorry, the second distillation column. Oh God. Okay, now this is it will be a good idea if we make everything at saturated condition. Can we do that? I'm not really sure. Sekejap kita tukar 300. Ataupun we put it in 0 and see what happen. Because this is already at condensed saturated condition, so does not really matter. So we are okay. So dekat 300, if you set it, because whatever coming out from distillation column ni, distillate ni is already at saturated liquid condition. Because tadi bila kita tukar this one kepada 0, your temperature is still minus 177, which is similar to this. So let's not manipulate anything. So now this is a binary distillation column. So when this is a binary distillation column, it's a good idea to for the stream inlet need to be at a saturated liquid system. Okay, so that's why I nak tengok the information tadi tu. Now let's bring in. So let's do this total kita buat total condenser sebab I dah try banyak kali. Berkali-kali I try. So and then suddenly I just realise it need to be total full reflux punya method. Bukan total dia akan jadi liquid kan. This one everything will be full reflux. I tak boleh nak paksa this one to make it as a liquefied. Dia punya utility dekat condenser is very very high. When I do that and then there are some of ketene dekat of the top bila I force this one at the total condensing. Bila total condensing maksudnya everything liquid kan. So kalau partial dia ada 2, but then the output in here is only methane. So there's no point of doing it in partial. So why I want to force it to be in total, because I want to keep methane in liquid form. Cryo punya system. But unfortunately it is not easy to do it in distillation column. So the best way to do it is to do it in the full flux. Faham ke apa saya cakap ni?
Faham.
Faham, good. Okay, 11. Q107, Q108. So your bottom, top is 12. So the bottom is 13. Next. Oh, before that, I don't know. Let's put it 20, 30. Next. Condenser pressure di boiler. Tadi kita 3 kan? So 2.3 bar, 230 bar. Tak apa baru masuk ni. Nombor masuk tu. Salah waktu ke? 230. This one is, I don't know, 130. Nanti kan kena letak kompresor lagi, never mind. So this one kosong 20 kPa. So 20 kPa. Next. Reflux ratio. Letak je lah nombor apa ikut suka you. Sebab kita nak dapatkan just degree of freedom tu. 0. Degree of freedom is equal to 0 again. Let's go to monitor. Kita add spec. Column component fraction. Add spec. Again, I suka nak specify dekat, you can either specify kat condenser or reboiler. So we might want to specify, let's specify this time dekat condenser. It's a mass fraction. It's in vapor phase sebab kita everything is went out kan. Yang methanol tadi tu, methane tadi tu. So it's methane. So what do we want? Methane is 99.5%. Because this is what your customer wants, 0.995. enter, close this, make this one as an active. We just don't care what is the vent rate like. Run. Why this is unconverged? Tengok dia jadi nanti 6.5. Dia jadi 1. Okay, we nak 1, kita bagi 1. Dah leceh lah benda ni. Let's change this to 0.995. That. Okay lah, kita tukar lah benda ni. I tak nak buat kat condenser. Let's dekat reboiler. This is mass fraction, vapor, 0.99. Product purity, methane, ketene, bla 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 bla. Dia sebenarnya yang kita set ni sama je. Okay, now kita pergi kat connection. Ni apa isu pun tak tahu lah ni. Let's change this. Kadang kena reset, kadang bila dia 2 kali bila dia macam pening. Oh God, what do you want? Ni temperature ni, dia nampak tak ada temperature ni after stage 5 ni, dia ada issue. You see? Dia dah jadi plateau like that. Dia patutnya like that. So this is where the issue. So we know that it might be with the temperature issue lah ataupun the number of stage issue. So let's change this one to 10 and see what happens. Sini pula. So probably the temperature in here, we have to increase it a little bit. 300. Yeah, minus 177 ni I think. That's the issue. But we already condensed it. Can we vaporize it? I don't know. Let's vaporize this. Kau sedap hati je buat Mesti you pening. Pening tak?
Pening.
Pening lah. Apa benda sekejap gitu, sekejap gini je. The issue with the temperature, I think because the temperature yang tadi ni dekat 11 ni is negative something tau. Jadi dia tak boleh nak converge. Kenapa lah awak tak nak delete? Enter. Enter. Okay now. So kita increasekan, kita jadikan dia two phase because obviously it's not working. Kita nak jadikan dia letak dekat saturated liquid. We need to increase the temperature a little bit because kita ada issue nak dapatkan temperature profile dekat temperature punya yang macam kita tengok dekat tadi kan yang graph temperature and apa ni temperature and stages tu. So we put in Q109 14 and see what happen. Okay, pressure drop, I don't know, 20. Temperature kita naikkan. Tadi temperature berapa lah? Temperature ni tadi? No. I don't know. Naikkan, katalah kita nak dapatkan 0.5. Still, because we are forcing methane to liquefy. So let's do this at, I don't know, 30 degrees Celsius. This is a liquid. When you have a liquid, it's necessary for you to put in a pump. Mungkin you can put heater first and then pump. Okay, that's not really matter. That one you tukar kemudian nanti. So let's change this one. I don't know, 350. Because kita ada increase of pressure dekat sini. So the temperature is 30. Let's see whether this is working. Oh, degree of freedom 1, memanglah. Okay, now 1. Okay, so really it's not working. So we add another one, component fraction. This one tadi dekat our distillate kan? So let's do this at our condenser. Now this is mass fraction in vapor because everything is vented out. So that's my methane. It's 0.99. Apa tadi? 0.995. 5. So run. Kenapa you tak nak running? Sekejap boleh, sekejap tak boleh. I pun tak tahu lah benda ni. Now, coming in 330, this is 200, that is 130. Let's change this to 100 and see what happens. Solvent. See, this is already 1 tapi dia ada issue ni kat sini. So, maknanya dah dapat dah, this is above that 1 actually. Oh, come on. Jadi isu kat sini. This is the feed tadi kan kita letak 15. Oh. Kita tipu sikit. Tahu apa dia nak. Tak mau juga. Apa benda dia nak ni, I pun tak tahulah. Hai. Tapi dah nampak tak you punya reflux ratio ni dah jadi tak logik. 1 times 10 of minus 5. dah jadi tak logik. So you cannot actually do this. Okay, let me change this. 0.995. I want it to be reset. I want to run this. This one looks fine. The temperature kat atas ni negative 160. Oh, even worse. So we have to increase the pressure. Tak tahulah apa benda dia nak benda ni. Sekejap. It's not a good idea. Dia rapat dah ni. Tapi dia tak nak converge because of the profile of the temperature ni. Oh. This. Okay now, macam ni. Because we are running out of time mana tadi? Ada tutup. What is it? Alamak. Oh shit. It's not the shit. Mana pula tadi tu ada tutup. Okay, never mind. Ni dia. Okay, now this one, if this one can be converged, then you will have the product parity dekat sini dengan sini. So what you need to do is that you have to put it in the this one, this methane. I kena buat sebab but then the time is running out now because sebelah ada gelas lain. So this one you need to appropriately store it. Methane has to be stored in the tank at cryo. So I think I put it in negative something lah. So this one you have to put it also in the tank. Kitin ni you have to do it also in the tank. Maknanya kalau you need to increase the pump, you need to increase the pressure and so on, you go ahead, because this one we are running this is a low pressure. But now the thing that I want to show you is how to do the recycle stream. Okay, so just ignore this. Nanti I akan share I punya apa ni, I punya output. So this one dia tak habis lagi kita maknanya dia ada kita dengan methanol. So you need to do the second separation. So now, okay, now when you want to do the recycle stream, you have to have a purging. You have to have a purging. So that means that you are going to put in a T inside here. In here, that's a T. Then this is inlet number 10. So that is 12. That is 13. Okay, now the parameter, the split ratio. Sebab kenapa kita nak the purge? Because if anything happen to the system, we can just close the you punya feed to the recycle. Okay, recycle ni close, then you open the purge ni. So but it is necessary. So but then for the time being, we set the flow ratio for purge is 0. Maknanya everything we make it go to the recycle stream. Now if you want to do this recycle stream, what you need to do is that you have to match your temperature and pressure ni sama dengan the temperature and pressure yang dekat sini. So now your temperature in here is 89.27. Your pressure is 280. Now your pressure in here is 3 bar. So 2.80 to 3 bar is very apa nak kata dia very close lah. So instead of putting in the pump in here, which does not make any sense, just to increase 0.2, so you manipulate you punya pressure kat sini. So you can actually put it 3 bar. Tengok macam mana jadi. We still got this. I think at 10 your composition is still 1. Okay, so now so we got 3 bar. So what we need to do is that to reduce the temperature to 25 degrees Celsius. So when we want to reduce the temperature to 25 degrees Celsius, so you bring in, sebenarnya benda ni boleh terbalikkan tau, but I tak tahu macam mana nak rotate. I can't remember how to do this. Why do we have this? Cancel please. So inlet 13, outlet 15, your energy is 107. Okay. Okay. And then remember you have to put in the parameters inside here. That is, I don't know, 20 kPa. 10 lah kot sebab dia sikit je. That's a tube side kan. Tube side 10. No, let's put it 30. Sebab nanti kalau you nak, yeah, you can do this, don't worry. And then the pressure, the temperature out here has to be 25. 25 sebab you nak matchkan dengan the one that you have. Or pressure dah jadi 290, so you tukar kat sini kepada 3 bar. 310. Let's change this to 30 bar because later on nanti you nak tukar kepada your heat exchanger kan. You have to match that with your heat exchanger. Kalau your tube side 30 kPa, then you let it be like that. So that this one you akan dapat 25 degrees Celsius and 3 bar. So you will have the recycle, what we call in here, it's basi-basiu ni ha. Now, type in here, recycle. So that's the recycle stream there. That's what it looks like. So the inlet is 15, the outlet is 16. Now, kalau you tengok dekat sini, dia ada composition ni dia memang as if macam kita buat kan. So 81.86 kilomol 4755, that's your composition. Okay, dia macam as if we plug in the new value, but then this is taken from the recycle stream dekat sini. So now we can actually masukkan dalam ni. Now, we want the total to be 8,000 kan? 8,000 kilogram per hour. So this one is 4755. So 8,000 minus 4755 will give you 3245. So this one you masukkan dulu. You bolehlah ikut suka nak on full ke apa. Stream berapa tadi? Stream 16. Oh, kenapa di iteration tu? Yes. Lah, patutlah silap. So patut ni stream 3 and then dia ada another one, stream 16. So stream 3 ni you kena tukar kepada 3245 because we have recycle stream. 3245 enter and we got that. So dia okay lah, dia dah recycle. So the key point when you want to recycle stream, make sure your temperature and pressure is the same. Yang masuk dan yang keluar ni. Yang masuk ni ke dalam tank. So that's it. That's it. Okay. Tapi ni lah kena buat isi balik. Penggeram ni kenapa dah tak boleh ni. Okay, it's 10:30 already. Nanti I akan share dengan you dekat dalam Moodle, I punya output yang daripada extended tu. Obviously my temperature and pressure ni ada sedikit perbezaan. So when you want to do your HISIS ni, kalau you ada isu macam I kan, I dah buat 3 kali ni, the third one pun tak dapat. It's not that difficult sebenarnya. It depends on your luck actually. So if you're lucky then you got it. So kena sabar lah, kena sabar. So along the way you will learn a lot from here. Okay. That's it kot. Ada soalan tak? Ada tidur ke?
Betul.
Ya.
Kalau isotropic distillation kan, possible tak dalam IC?
Possible. Isotropic, alamak. Okay, now kalau you guna isotropic distillation column, usually the best way you cari pressure swing, pressure wing distillation column. Maksudnya you ada 2 DC tau.
Dia main dengan dia lah.
Dia main dengan pressure. Dia satu DC pressure tinggi, satu DC pressure rendah.
Oh, kena buat distillation column punya train tu lah. Kira macam
Kena buat train.
Oh.
Kenapa? You punya ada ni ke isotropic ke?
Kalau dual pressure ada isotropic, kalau yang single pressure nya just absorption column nya. Tapi tu lah
Absorption column student, okay,
proses.
minggu depan I akan invite student design project I untuk buat presentation kat you on macam mana dia buat experience lah, sebab I kan lecturer, you dengan student ni elok dengar pada student sendiri senior you kan. So dia punya proses production of hydrochloric acid memang ada absorption column. So bila dia ada absorption column, I pun tak dapat selesaikan benda tu, but he did it. So dia buat sendirilah. So I suggest guna dia guna cutter, dia guna different fluid package. Maknanya untuk dia buat dekat absorption tu je, dia kena buat different fluid package, and he has to do it at very high pressure. So next week pukul 11 kan, so I'm going to invite him lah to give some presentation to you guys.
Oh, okay. Saya nitric acid by the way.
Lebih kurang kot dengan hydrochloric acid tu.
Maybe aku.
That's why dia guna pressure dia very very high, but then the issue with dia tak dapat actually lah, the comment daripada panel and also the comment daripada pensyarah yang mark dia punya proses tu, dia nak minta proof why is that the pressure is being carried out at why the absorption is being carried out at high pressure. Sebab bila TED dia buat, nama dia Syati, bila TED dia buat banyak kali punya simulation, then he found that it can only be separated at high pressure. Tapi dia guna Kessler, saya tak ingat lah apa benda, nanti you tanyalah kat dia minggu depan. So dia guna fluid package yang lain lah daripada yang ni, sebab dia masuk, sebab dia very ionic tau, because you guys you guna HCl kan. So macam kalau nak guna Pan Robinson tu dia macam pening sikit lah, dia nak estimate because that is ionic. Kalau ionic elok guna activity coefficient model.
Oh, okay.
So antara activity coefficient model tu pula, kalau you tengok macam Wilson tadi, there are some interaction yang dia tak ada binary coefficient tu. So dia assume kosong. Jadi it cannot really accurately ni lah. Tapi itulah I kesal lah dengan group I because dia tak ada apa-apa reference yang saying that to separate the high pressure. Dia memang tak boleh nak justify benda tu. Tapi HISIS kata feasible. So macam mana kan dia nak
dia nak justify benda tu tak boleh lah.
Apa dia?
Nak justify benda tu tak boleh lah.
Kalau ada reference okey, tapi dia tak boleh nak justify. Panel memang tanyalah. Senyum je lah. Jumpa. Senyum je lah. Memang tak jumpa. So HISIS kata feasible. Dah lah running at a high pressure kan. So berapa? I think 200 bar kot.
Oh, tinggi lah.
Tinggi. Tapi fluid package yang biasa tak boleh guna. Dia
dia guna
dia akan guna cutter. So I akan minta you dia ni lah, dia guna cutter, and then next week I think kita akan go through the pressure drop across the plant. Kita akan go through the HISIS punya requirement. Allah Akbar. Design project punya requirement yang untuk HISIS tu.
Okay.
Kita akan go through satu-satu. I mean how you can get high marks for that lah.
Okay. Betul?
Ya.
Kalau like macam saya ada macam recycle stream tau. Recycle stream dia recycle masuk the same heat exchanger. Yang tu macam mana? Macam dia recycle, so dia guna like macam saya punya keluar dia
keluar pada mana ni? Apa benda?
Daripada absorption column. Dia keluar as tail gas tau. So dia guna balik tail gas tu as utility untuk heat exchanger tu. Saya tengok PFD dia.
Dia dah pinch lah, dia dah pinch.
Dia dah pinch. So like
macam ni. Dia secret dia macam ni. Apa kata untuk DP1 you jangan pinch apa-apa dulu.
Oh, okay.
Sebab you pinch ni untuk DP2 kan? DP2 nanti you akan ada perubahan PFD.
Oh, improvement sebelah.
Kalau you buat siap-siap ikut pinch, you akan nanti calculation you macam tak banyak beza before and after pinch.
Oh, okay.
So kalau I kata kat student you biar je dulu untuk DP1 sebab kita tak akan tengok requirement untuk pinch tu. Tapi kalau nak buat tak salah, it's good to do it. Tapi cuma nanti pinch je lah number of number of heat and cold exchange 0. Tak best lah. At least kalau dapat, we can reduce what is the cost we can reduce because number of heat exchanges we can reduce is 3. Syok sikit dengar kan?
Betul kan?
So jangan pilih dulu. Tapi sebenarnya kalau nak recycle, anything you need to recycle, you kena letak R tu, recycle tu. Kalau tidak nanti dia akan pening.
Alright.
Okay.
Thank you, Dr.
Right. Anyone else?